So I'm happy to introduce our next speaker, Noelia Bortolussi, from Universidad Nacional de San Luis, that will tell us about the adjoint algebra for two categories. Thank you, Noe.
Okay, thank you very much, Julia, for the introduction and to the organizer for the invitation. So as my title say, I'm going to talk about the adjoint algebra for two categories, but I will start with some introduction. So as you know, there are categories that they are built using methods from two categories, or maybe you can take the categories and move them to the world of two categories, and then you can see maybe some things easier to understand there. So we're interested to the study of the adjoint algebra, which is a complete invariant for module categories. So this work, that is a joint work with my supervisor, Martin Bombelli, it was born from the idea to compute the adjoint algebra for certain categories. So in particular, we are looking graded categories for a finite group. So at the beginning, we didn't have any idea, intuition, nor tool to do it. But in the middle, we came with the idea to move to two categories. So and see if from there we could find some way to compute this adjoint algebra. So the first that I want to show you is the definition of the adjoint algebra for an exactly decomposable C model over a finite tensor category. So for the whole talk, C will denote a finite tensor category over an algebraically closed field, and M will be an exact indecomposable left C model category. So the definition of the adjoint algebra for M was given by Kenichi Shimizu in 2019 and is the following. So the adjoint algebra for such a module category M is defined as the end of the internal home between M and M for M in the module category. And this is an object in the center of the tensor category. So it came with the natural transformation that we denote by pi M. So the adjoint algebra for the tensor category of C is the algebra AC, where C is seen as the regular module category. So this is an object in the center, so it came with the half braiding that is defined as follows: is the unique morphism sigma M, such that this diagram commutes. So that means that the half braiding depends of the denatural transformation, and we have here these two morphisms A and B, where B is just the morphism that allow us to put this X inside the internal home with the dual, and then it's combined with an evaluation map for in order to go from this object here to this object here in the middle. And this morphism A is just the monoidal structure of the functor internal home M empty space. So this is the half braiding, and the algebra structure is given as follows, is defined as the unique morphism M, such that this diagram commute. So the product depends of the denatural transformation, and here we have this morphism comp that is just the canonical structure, algebra structure of the object internal home between N and M. And the unit is defined as the unique morphism UM, such that this triangle commutes. So here we have the denatural transformation, and here we have this coef morphism that for any X, this coef map is just the image of the identity of X acting on M under this isomorphism C, that is just the isomorphism that came from the definition of the internal home. So this is the adjoint algebra for an exact indecomposable module. So what we want to do is try to do the same for two categories. So try to define an adjoint algebra for two categories. We are interested in some special two categories that they are finite. So from now on, B will be a finite two categories. So in the case that you don't know what this means, this is just a two categories where the home categories are all finite and the identity is a simple object for any zero cells A. So if you take two zero cells, A and B, we are going to define a zero cell as follows. Take the end between x dual composed with x for x, an object in the home category AB. So this end is an object that belongs to the home category AA. So this is the usual end. And this came with the natural transformation that we are going to denote like this, pi to the AB, to refer that we are working in the home category AB. So if we fix the zero cell B, and we consider the collection of all these ends for all A, then turn out that this object is an object in the center of the two categories. So it has a half rating that we denote like this, like sigma to B. For remember that B is fixed, so we denoted the half rating like this. And moreover, if you consider this collection together with the half rating, and you call it ADB, then this ADB is an algebra in the center of the two categories. So the algebra structure is given as follows. The product is defined as the unique morphism such that for any A, you should take in mind that since ADB is a collection, the product and the unit should be a collection of maps. So they are defined as the unique morphism such that for any zero cell A, this map A to B A commutes. So and the unit is defined as a collection such that for any zero cell A, this triangle commutes. Where here we have this coef that is the usual coevaluation of the object X in the home category AB. So okay, we have an algebra in the center. So we define the adjoint algebra as this collection, the collection of all these n together with this half rating. So at this point, you have so many questions about this definition. So let me guess some of them. Maybe the first question that you have is what happens if we take zero cells A and B, which are equivalent? So what happened with the adjoint algebras? Maybe they are related or not. So the answer is what you expect, that they are isomorphic as algebras in the center of the two categories. So this is the easy question. Maybe a harder one is that what happens if you suppose that you take B and B tilde to find the two categories, and you have two equivalences between them, and you compute both adjoint algebras for the both two categories. So what happened with the adjoint algebras? So for answer this question, you need to know that if you have any B equivalences between B and B tilde, it induces monoidal equivalences between the centers. So knowing this, we can answer our question to say, you take your two equivalences, you take the associative monoidal equivalences, then for any zero cell B, you have that if you compute the adjoint algebra, of B, and then you apply the associated monoidal equivalences, this is isomorphic to compute the adjoint algebra of f of B. And they are isomorphic as algebras in the center of B tilde. So what we are saying is that if we have two equivalences, we are sending adjoint algebras to adjoint algebras. Okay, that this is really, really nice. But I think that the main question is if we have a way to recover the J-Mitsu adjoint algebra. So what about if we compute the adjoint algebra for the two categories of C modules? Okay, the answer of this question is one of our main results of our work. And for that, we need a theorem that says that there are monoidal equivalences between the center of the C module with the center of the exact C module and with the center of C with the reverse tensor product. So with this result, first if we find these monoidal equivalences, the second one, and you take an exactly decomposable left C module, and you compute the adjoint algebra, and you apply these monoidal equivalences, then you recover the J-Mitsu adjoint algebras, and they are isomorphic as algebras in the center of C. So we recover the J-Mitsu adjoint algebra, so we can say that we have some kind of generalization of this notion. But okay, you generalize the notion, but what does this new notion give us? So do we get something new? The answer is yes, we have something new, and we have new result about finite tensor categories. So a first result is an immediate consequences of what we see. The first result that we saw, that this is this one. If you take M and M equivalent exact C modules, so you have that the adjoint algebras, the J-Mitsu adjoint algebras, are isomorphic. So how you can prove this? Well, it's easy. You take the two category of C module, then M and N are zero-cell there. So you have that the adjoint algebras are isomorphic, where M and N are seen as objects at zero-cell in the two categories. So we can apply the previous theorem with this monoidal equivalences phi, and then you get that the two J-Mitsu algebras are isomorphic. So this result is almost immediate. But the more interesting result is this one. So if you take C and D finite tensor categories, and then an invertible CD module, you have a pseudo-functor which is defined like this. So we are going to denote it by theta to the n, and it's something that goes from the exact C module to the exact D module that take a module M and send it to the C module functor between N and M. And if you take a C module functor F that goes from M to M prime, this the functor send it to a functor from the C module between N and M, the C module functor between N and M, and the C module functor between N and M prime. And it's just decomposition with F. These pseudo functors turns out that is a two equivalences. So this fact is something that is not easier or immediately to check, but we have a two equivalences. So as we saw before, this induces a monoidal equivalences between their centers, and we are going to denote by theta hat to the end this monoidal equivalence. So now take a particular tensor category D, take D equals to this dual category. And if we do that, we have a commutative diagram of monoidal equivalences as follows. We have the monoidal equivalences 5 in the vertical arrow. Here in the bottom, we have this theta hat. And here we have this theta that take an object in the center and send it to the end effector, theta v sigma, that if you apply it to an end, is just a v acting on n. So take in mind this diagram and take n an invertible DC bimodule, an m an indecomposable left-SXC module. Then you have an isomorphism of algebras like this. If you compute the Shimizu adjoint algebra and you apply this equivalence theta, then this is isomorphic to the Shimizu algebra, adjoint algebra of the C module functor between n and m. And I would like to show you a sketch of the proof that if is the following. You have this theta am. So we go back to the diagram, and this is an object here. So we can, in the place of we consider theta am, we go here and we compute the adjoint algebra here, and we can send it with this theta hat here to this center, and then we can play with the monoidal equivalences phi. So in the place of write theta am, we can write phi of theta hat n of the adjoint algebra of m. Since this theta hat is a monoidal equivalence, it is an induced one. So by the theorem that we saw, that what happened under two equivalences, this is just the phi of the adjoint algebra of this theta hat m, that is just phi of the adjoint algebra of the C model functor between n and m. And then for using the correspondence theorem with the Shimizu adjoint algebra, you have that this is isomorphic to the adjoint algebra of the C modulus functor between n and m. So with this generalization of the notion of the adjoint algebra for two categories, we get some new result, and we hope that this can help us to compute the adjoint algebras that we are interested. So that's all I want to tell you. So thank you very much for your attention.